Great. Hi, my name's Matt Spitz. I work at the eBay New York office via the Hunch acquisition, and I'm here today to talk about practical machine learning in Python. So it is a tired expression, but it's true. This is the age of data. As it turns out, data is everywhere. You can get it from your application logs. You can pull it in from external APIs. People are notoriously bad at managing their Facebook permissions. And there are a number of public data sets available for you to use. There's value in learning about your data. You can learn how people use your site, what kind of people use your site. You can do dynamic optimization, which features to show particular users how people respond to different aspects of your site. And one big enabler for all of this is that storage and CPU time these days is really, really cheap. You don't have to own a really big system or have a ton of storage capacity. You can just throw it up on S3 and rent a machine for a few hours to process gigs and gigs of data. It's great. So in Python is a fantastic programming environment for data processing and analytics. It's incredibly versatile. On one end of the spectrum, you can write quick and dirty scripts to, munge your data together, process it, coalesce it, whatever, or you can build full-featured real-time applications to serve up whatever your results are. There are a wide variety of off-the-shelf toolkits that you can use. There's a ton of choices. Then they range from plug and play, so just in 3 lines of code, throw your data in there and see what you get, to various building blocks that you can use to build your own machine learning components and build your own applications. So in this talk, I'm going to be discussing one flavor of machine learning called a classification problem. And I'm going to go over some basic terminology just so we're all on the same page. Your data set is made up of data points, which are considered to be, in a classification problem, a feature set, which is a series of interesting facts, for some definition of interesting, about some event or thing, and a label, which is a description of that event or thing. And in classification, you take what's called a training set, which is a bunch of labeled feature sets, and build a classifier which will allow you to predict labels for unlabeled feature sets. So that's a lot of words, but the intuition is that a training set is what you know about the world, and you train up a classifier to predict things that you don't know about the world. And to illustrate this, and hopefully the problems that I'm going to go over here are maybe similar to ones that you might have that are more directly applicable to your products or your businesses or whatever. But as a concrete example, I started playing around with some baseball stats to illustrate how one might build a machine learning application in Python and how to go about it. And even if you're not into baseball, you know that the iconic visions of success and failure are the home run where the batter hits it all the way over the fence, or a strikeout where he goes back to the dugout in disgust. In the movies, it's the equivalent of getting the girl versus, being the villain, whatever. So in this setup, in this application I wrote, I have 2 questions. Question number 1, what features are strong predictors for home runs or strikeouts? And question number 2, given a particular situation, with what probability will the batter hit a home run or strike out? These are 2 separate questions, and I answer them independently. Going back to what we were talking about earlier, the feature sets for this problem represent the game state for a plate appearance. So given a very particular situation, what is the outcome of that plate appearance? And in my case, the features are things like whether it's a day game, whether it's a night game, whether the wind is blowing in or out, what inning it is, how many strikes there are in the count, whether it's a lefty batter versus a righty pitcher, or if they both bat left and right, throw left. There's also stats about the players themselves. You have the batter age, the pitcher age, their weight, what position the batter plays in the field, how many years of experience they have, even things like where they were born. And so the labels for these particular situations are simple. It's either the batter hits a home run, or they strike out, or something else. And to make it a little bit more concrete, going back to the example before, we have a training set which consists of blobs of data like this. So we have Obviously there are more than just these three, but consider that we have some situation that we know about where it was a day game, the batter was age 24, the pitcher weighed 211 pounds, and that plate appearance resulted in a home run. In another situation, it was on a day game where the batter was age 36, and the pitcher weighed 242 pounds, the batter struck out. And in a third situation, a night game, batter is age 27, pitcher weighs 195 pounds, something else happened. We have tons and tons and tons of these data points to train up a classifier. So now we look at future situations where we don't know what's going to happen, and we predict. So, for example, if it's a night game and the batter's age 36, then the pitcher weighs 225 pounds, what happens? Well, our classifier might predict something like, well, there's a 2.6% chance that they'll hit a home run and a 15.6% chance that they'll strike out. That's how classifiers talk, by the way. In another situation, given that it's a day game, whatever, you can read. The classifier might say something like, well, there's a 2.2% chance it'll hit a home run or a 19.1% chance that it'll strike out. Great. So this is a sort of framework in which we'll be answering these questions and the sort of way that you want to set up your problem. But before you can even set up your problem, you need to go and get some data. And I was saying earlier, the data can come from your own application logs, can come from external APIs, just public data sets, whatever. For this problem, I pulled in the data from retrosheet.org, which is play-by-play logs for every game since 1956, which is pretty cool, and Sean Lehman's baseball archive, which contains detailed stats about individual players. And just starting with these data sets, we can't plug them directly into a classifier. We need to convert them into some classifier consumable format and come up with these feature sets with labels. So the first step is coalescing this data into whatever we consider to be our valid and interesting features. So in the first pass, I ripped over the Lehman data set and created a database of player ID to details about that player. And as a side note, I found the shelf module, which I used for the first time, which was really very useful. It was in terms of storing like persistent dictionaries on disk. End of the side note. In the second pass, once we have this player database, I ripped over the retrosheet logs, and for each play, I kept track of a current game state, and with every outcome I saw, I outputted a feature set, joined up with the player DBs for particular details on whether, what age the pitcher was or how much the batter weighed or whatever. Once you have this data set, though, you're not quite done. As it turns out, when you're dealing with lots of data, and this is a cause to hit your head on the table many times, there are inconsistencies in that data, or it's malformatted or whatever. So you need to I did a second pass where you went through and made sure that all the values were logical. Like you can't have the number of strikes in the count be something like fish, like it just doesn't really make sense. So you either need to throw out or resolve those inconsistencies. And in the end, I came up with a training set with all the regular season games from 1980 to 2011, which is about 5.7 million plate appearances, 135,000 home runs, and about 871,000 strikeouts. Cool. So now that we have all this data, we need to find something to apply to it, right? We need to define how our classifier will interact with that data. And in Python, there are some trade-offs, or in any machine learning context, there are some trade-offs in considering which toolkit to use. One trade-off to consider is speed. What are the deadlines on how quickly you need to get these results? Are you just trying to find some correlations and trying to find some interesting aspects of the data? You're just trying to come up with some pretty graphs? In that case, your deadline is probably on the order of hours, days, or weeks. But if you've got a real-time application, you've got a user sitting on the other end of that request, waiting for your classifier to make a decision to personalize a page for them, for example, then your deadline is on the order of milliseconds. Your problems are different, but this is just something to consider in general. Another trade-off to consider is how transparent the toolkits are. At some point, you may want to know what's going on under the hood, and you might want to optimize it yourself and customize it. How easy is it to do that? Can you actually go and dig in and see what's going on and change it, perhaps? And a third trade-off is how much support is there for this toolkit? How mature is the toolkit? Is it under active development? is, are there sufficient documentations and tutorials available? If you have any questions or if you fix a bug, what's the community status look like? At a high level, you basically have three options in Python. You can use external bindings to existing packages. So there are some really popular and well-tested and well-used statistical analysis packages like MATLAB or R, Octave, or the Shogun toolbox or whatever. And Python has bindings to those. So they don't necessarily add a lot in terms of functionality to those packages that already exist, but they give you an interface to work with the data structures or work with the way that the code you write is interpreted. This is useful if you've done some analysis already in one of these tools and you want to transition your workflow or your machine learning to Python without too much of a hassle. Again, you can swap that component out later, but for now, let's just bind to what we have already. Your second option is to use a Python-based toolkit. There are a number of these toolkits, and I'll talk about that in a sec. But they represent collections of algorithms, mostly written in Python. And some of them use external components, maybe C bindings. Some of them even use other toolkits. They're just aggregated sets of machine learning tools, usually with a similar format or a similar way to interact with them. And your third option is to just do it yourself using various building blocks. You can use these external subcomponents. You can write it entirely in Python if you want. But that's just another option. So let's talk about some Python toolkits. I want to give a sampling of what's available, and to do so, I chose some toolkits that were updated. Their last update was within a year. As a disclaimer, this is not an exhaustive set, it's just a sampling. Some of these tools I've used, some of these tools I haven't, and I guarantee you that I'm missing your favorite, and for that I apologize. One thing to keep in mind is that different packages do different things, so it's, one of these is not going to be your Excalibur. You're going to want to, Excalibur? Silver bullet? Whatever, analogies. So one of, metaphors? Metaphors. Whatever, here we go. The first one I want to talk about is NLTK, or the Natural Language Toolkit. NLTK focuses on natural language processing, naturally, and contains a number of algorithms for text processing, like stemming, or you can do classification, you can do clustering. Mostly written in Python, and there's a pretty big visibility into what it's doing. The nice thing about this one is that there's a book that goes along with it. So if you pick up a copy of the Natural Language Processing with Python book, it'll walk through some of the concepts of natural language processing and using examples from the NLTK toolkit. So it's sort of teaching you how to use a model and what it does at the same time. Another package that I haven't played too much with but seems to have a lot of options is MLPy, which has a bunch of regression algorithms, classification algorithms, clustering algorithms. The oppositely named PyML focuses on support vector machinery and other kernel methods. If you're interested in doing neural networks, PyBrain might be a good option. One that I thought was kind of interesting was the MDP toolkit, the Modular Data Processing Toolkit. A lot of these toolkits have individual components that you can use, and it's up to you to sort of string together how you want your data workflow to go. But MDP allows you to construct a whole workflow with nodes and dependencies on those nodes. So you can string together your entire workflow all within the context of the same toolkit. And it allows you to do the scheduling and perhaps parallelize them. I thought that was pretty interesting. The last one I want to talk about, I saw some buzz around at PyCon last year, and I've checked it out recently. It's actually been built out a lot, and then there's a lot of excitement around it. I think there was even a tutorial yesterday. But scikit-learn has a huge variety of algorithms using supervised learning, unsupervised learning, feature selection, visualization, all sorts of stuff. It's under very heavy development, and there's a very large team working on it. The documentation is excellent, the tutorials are excellent. There's a very active community on mailing lists or IRC you can get in touch with if you have any questions. I think this is going to be a pretty exciting thing if it's not already. And it was something to consider if you're looking into this. If you don't like any of those existing toolkits, you can always build it yourself. Almost every single Python toolkit is built on the two basic building blocks of NumPy and or SciPy. NumPy is fast and efficient arrays implemented in Python. And SciPy is a number of algorithms built on top of NumPy, which allow you to do a lot of very standard stuff. You can also use C or C++ implementations. There are a lot of popular algorithms like liblinear, libsvm, OpenCV, all have Python bindings, so you can just plug in and do it yourself, or plug in and interact with them. Another option is to write your own components. And the nice thing about Python is it's a very modular language. So if you're using one of these components from a toolkit and it turns out the implementation isn't cutting it, you can rewrite it yourself in C, and just, as long as it has a similar API, you're all set. So cool. Lots of talking. Let's show some stuff off. As an example of applying these toolkits, let's go back to my 2 questions. Question number 1, what features are strong predictors for home runs and strikeouts? And given a particular situation, with what probability will the batter hit a home run or strikeout? The first question, perhaps by design, is an excellent candidate for what's called feature selection. Feature selection is something you can do offline to identify predictive features. And a predictive feature is one that is strongly correlated with a particular value. So for example, if you're considering the home run case, it might be predictive that this player can maximum benchmark this many pounds versus that player who can benchmark a certain other number of pounds. A not very predictive feature is what favorite cookie a batter's is. And maybe there's some argument about peanut butter cookies and protein, but that's beyond the scope of this discussion. So, I just cracked myself up. Anyway, so the idea of feature selection is to suss out the predictive features or the not predictive features. And for this, I used scikit-learn's chi-square feature selection algorithm. Super simple, converted all my data points into vectors and ran it through and saw what came out. And to see what came out of it, I made some pretty graphs. And these graphs are, for a given feature that's significant, for every well-supported value, I found the correlation with hitting a home run or striking out. And a well-supported feature is one for which at least 0.05% of the samples had that feature with that value. So it's a notion of significance. And chi-square sort of does this under the hood, but as when I was drawing my graphs, I ripped over the data again to take a look at it. And the correlation is defined as, the probability of a particular event given a feature equal to a certain value over the probability of that event occurring with no other knowledge, -1. And the intuition there is, if you're more likely to hit a home run, given this particular feature, then the correlation will be positive, and if you're less likely, it'll be negative. Okay, so let's take a look at some graphs. All right, it's big enough. So there's a common intuition that if you're the home team, you have an advantage. You're playing in front of your own fans, you're playing at your home ballpark, whatever. And this actually comes out a little bit. There's a slight correlation between hitting home runs and being on the home team, and a slight negative correlation between striking out and being on the home team. And the opposite is true for the visiting team. Great. This is what we call a sanity check. Another graph that's interesting is the correlation of hitting a home run or striking out based on what position you play. And everybody knows that pitchers are basically automatic outs on that far left column, and you can see that those bars are actually doubled in length. I just didn't want to blow out the scale of the graph. And you can see, first basemen are more likely to hit home runs than they are to strike out, et cetera, et cetera. And a lot of that is not causation. Certain positions are more difficult to play than others, and so you'll sacrifice hitting ability in order to get someone who's good at fielding. But the one interesting thing is at the very end, you have the pinch hitter, which I identified as a fielding position. And a pinch hitter, for those who don't know, is someone who's put in a pinch to substitute for someone else. And they are much more correlated towards striking out and much less correlated towards hitting home runs. And maybe that's because it's a tense situation perhaps and they've never seen the pitcher before. Or it could be that they, if they were good enough to start, they would. Another interesting graph that I really hadn't expected is the temperature of the game and how that affects the likelihood of various events. So there's, as temperature increases, you're more likely to hit a home run, but it doesn't really affect how likely you are to strike out, except on really warm or really cold days. I can't really explain this, but it was interesting to see. And as a last graph, it's pretty comical. The year in which a game is played is a strong predictor in terms of whether people will hit a home run or strike out. And as you can see, in the late 90s and early 2000s, when people were juicing all over the place, there was a much higher likelihood of hitting a home run, and which has since tapered off. These people have been caught. Well, not all of them. Anyway, so the interesting thing about this graph is the strikeout correlation here. For whatever reason, and I can't explain this, and I'd love to know why, the strikeouts have become increasingly common since 1980. I don't know. These are the sort of things you can suss out of your data, and maybe you can try to explain it later, but like a technique like feature selection will allow you to do this. Okay, so the other problem I had was real-time classification, which is given features, let's predict some label probabilities. And for this, I use the Natural Language Toolkit's naive Bayes classifier. Ripped over the data, set up a training set, built out a classifier, and threw it on Gunicorn behind Nginx. And was that a woo for Gunicorn? Yeah, okay. So let's look at this. So what you would do is you'd set up a series of features. So let's say it's the sixth inning, the wind is blowing out, we've got the shortstop is up, and they weigh 185 pounds. Boom. The baseline probability, if we didn't know anything, is this little pie chart here, where they'd be 15.4% likely to strike out, 2.4% likely to hit a home run. That's just on average, this is what we've got. Given this particular set of features, the likelihood that that person will hit a home run is slightly less, and the likelihood that they strike out is slightly less. And you can see that a little bit better in this correlation index down here. So imagine if you're a coach and you're like, wow, okay, let's see, should we have the shortstop who weighs 185 pounds, or should we maybe throw in the third baseman who weighs a big boy, 275 pounds? Wow, it looks like that person is much more likely to hit a home run than strike out. And this is pretty quick because it needs to be quick, right? If you're a coach and you're making decisions, baseball is slow, but it's not that slow. So, this would be another sort of use case that you could do on-the-fly data analysis, and potentially, if we had some program that was deciding who should be batting, something like this would be a quick interface for it, and because the speed restraints are actually rather restrictive. Okay. Great. So we've talked about two problems and sort of things you can do with it. Let's talk about some basic tips and tricks. These are mostly applicable to Python, but I think they're applicable regardless. So remember how we had this nice little web application that allowed us to, to predict a particular label given a feature set. And as what we said before is that to create a classifier, we need to burn over the training set and create a model that represents what we know about the world. And that would be a real pain if we had to go over the entire training set and train up an entire classifier every single time we started the application. So one tip is to persist your classifier internals as much as you can. So once you've trained something, find some way to save it to disk. And this goes back to our trade-offs before. It really depends on your implementation. Some classifiers may expose this to you, the ability to dump it to disk. Others might not. Sometimes there's sometimes there's even a nice little method, which is like, this is how you build me, and you can feed it, build me from the thing from which you can build me, and it just works. Sometimes you can create your own by digging into the internals and figure out what constitutes building a particular classifier. But in the end of the day, persisting them really helps. Another tip is to use generators wherever possible. If you're ripping over lots and lots of data, that data, well, there's lots of it. So if you try to fit it all in memory, there's a limit to how much data you can process. And one way to do that is to use, if you can, use algorithms that are single pass. So for example, the Bayes classifier I used is a single pass algorithm. When you're looking at data point number 40, you don't care about what data point number 39 was. Some algorithms require a conversion pass before training, which actually ends up in a much more compact data set. So as you recall before, we had game equals day, night, like batter age. That's like very wordy. And at the end of the day, maybe all the algorithm needs is a numerical vector. So what you can do is either, as you're converting it, throw away the raw data, or do a full conversion pass at first and just convert it to a bunch of vectors before feeding them into your algorithm. The third thing I want to talk about is multi-core text processing. So when you're doing your data processing at first with your coalescing or whatever you're doing, you're scrubbing, typically you're going over these text files and you don't really need to look at more than one line or two at once, which has a pretty low memory footprint and in fact is very CPU bound. So what ends up happening is that you peg one core at 100%, and then you have 3, 4, 5, 6, 7 other cores that are just waiting for you to play Minecraft. So you can take advantage of those other cores using something like the multiprocessing module, or using just different Python processes that take different file names as input. All this makes your iteration of building this stuff a lot faster, and takes less time in the long run. So I hope this was helpful, but there is some fine print. This plug and play stuff is really easy, and increasingly so. There's a number of great toolkits that allow you to do this stuff without really understanding what you're doing. And that's okay, but you can't really blindly apply machine learning and hope that it just works. At the end of the day, you really do need to understand your data and understand what goes into it. And you need to understand your algorithms and how you're processing it. If you would like to learn more about your algorithms, one good resource is mlclass.org. It's a free class, and it provides a great foundation and a starting point for understanding ML. I think they did their first run this past fall, and it was, to universal acclaim. So anyway, so once you've got your data, once you understand your algorithms, you too can be a number muncher. And crunch and munch and do whatever those number munchers do other than get eaten by troggles. So anyway, thanks. The GitHub is for the SluggerML stuff is up there. It's kind of a mess. I apologize. I had a kind of chicken and egg problem this morning where I could post the slides before I had the link. But the slides are up there. And I'm Matt Spitz on the Twitters. And I'll take any questions if you have any.
If you have any questions, can you please form a line behind this mic and talk into the mic so we can get you on camera? Thank you.
Hi, so I was curious if any of the classifiers had, or the toolkits had the sort of highly specialized classifiers like maximum entropy models or things like that. Are those available?
They are.
Oh, cool.
I think actually the NLTK TK, Natural Language Processing Toolkit, does have maximum entropy classifier.
Do you know if any of these toolkits are GPU enabled?
I don't know. I imagine, I don't know. I'm not sure.
Another question, do any of these use restricted Boltzmann machines? Gregory Hinton's work on restricted Boltzmann machines, by any chance?
I don't know. That? Sorry.
Okay.
Do you know any toolkits that work on MapReduce frameworks like Hadoop and things like that?
Yeah. So there is, God, I'm blanking on the name. There was MR. Are you talking about like orchestrating MR jobs or?
Yes.
Yeah, I think, I forget who it was. Some company open sourced Mr. Job or MR Job, which would allow you to do something like this.
Yelp.
Yelp?
Yeah.
Cool. Yelp.
It looked to me like you binned the weights for the prediction problem. Can you say how you determined the bin sizes?
Excuse me? Oh, yeah. Heuristically. Just what was off the top of my head. Sorry.
Did you try to fit any kind of distribution to that? Or?
I didn't. No. Sorry. This was just a quick example to hopefully get something up. And it was working on it even till last night. So anyway, it seems like there's no other questions. So thank you so much. I really appreciate it. And enjoy your lunch.